Merci beaucoup, Fazia. Bonjour à tous, à toutes. Je vais, vu qu'il y a les collègues qui ne sont pas très francophones, je vais faire en anglais. Thank you very much for inviting me. I'm discovering a lot of interesting things because I'm not in the... je suis pas thermicienne. So today I will try to entertain you with Bio-Aerogels. So definitely you know what is thermal insulation, but probably you don't know what are Bio-Aerogels. I will start with presenting my lab. So I'm from the School of Mines of Paris. It is a higher education in France. It is one of the oldest universities or engineering schools in France, which was founded before the French Revolution, where there was a need in mining engineers. Since that time, there are no mines in France anymore, but the institution remained. And there are 17 research centers. 17 research centers belonging to École des Mines de Paris, and 5 are in the southern part of France. Near Nice, it is called Sophia Antipolis. Sophia Antipolis is a science park. It is not a geographical city. That's why you cannot find on the geographical maps, but it exists. There are about 40,000 people working there in high-tech companies, computer science, and so on. So there are 5 research centers that are located there, belonging to School of Mines of Paris. So one center is Center for Materials Forming. We are trying to do excellent research. We are collaborating a lot with industry, and our mission is education via research. We are not very large. We are about 50 permanent staff, half researchers and half technical staff and administration, and majority is of the population that's PhD students and postdocs. And we have 2 doctoral programs in materials, in the numerical simulations, and we have 1 postmaster program. So Center for Materials Forming, which type of materials we are working with? We are working with metals. Oops, sorry. We are working with metals and with polymers. And we are doing experiments, physics, materials forming, and numerical simulations. What we are not doing chemistry, so we are collaborating a lot with the chemists. This being said, I will switch to the topic of my talk today, and I will start explaining to you what are aerogels. If we want to know what are bio-aerogels, I will introduce what are aerogels, what are bio-aerogels and how they can be used, and what are the properties in terms of thermal conductivity of aerogels and bio-aerogels. So what are aerogels? Aerogels are dry networks, dry materials with very low density, very small pore size, definitely below 1 micron. But the pore size is of few tens of nanometers to few hundreds of nanometers. And due to this, they have very high specific surface area. Specific surface area is the sum of the areas of all internal pores. So it can go up to several hundreds of square meters per gram. That's huge. And this is what is making difference between aerogels and foams. Foams are lightweight materials, but the pores are huge. And with large pores, you cannot have high specific surface area. And what I'm always asking to pay attention when looking at scanning electron microscopy images is to look at the scale. So the scale is usually a few hundreds, 100 nanometers. You see the pore size. There are a lot of confusions about aerogels. The starting confusion is the definition of EUPAC, International Union of Pure and Applied Chemistry. The definition is old, not valid anymore, because it is saying that it is that aerogel is a gel comprised of microporous solids. Micropores are below 2 nanometers. So that's not okay anymore, and I'm in the working group to change this definition. So it is under the construction. The same UPACA, which gave the wrong definition, but named aerogels in 2022 among 10 emerging technologies in chemistry. Okay, so that's a fashion in a way, the aerogels, and they can have different type of shapes. So in the word aerogel, there is a gel and aero. So you start usually with a gel, which means there is a liquid inside, and we want to evacuate the liquid, not perturbing the morphology of the network. So how to do this? If you are doing evaporative drying, this was explained well yesterday. If you are doing evaporative drying, there is a capillary pressure that is developed, which depends on the surface tension, on the contact angle between the liquid, evaporating liquid, and the pore, the matter of the network, and on the radius of the pores. So if we have a nanostructured network, the capillary pressure will be very high if you are just leaving your gel evaporating in the ambient conditions. What to do? How to overcome this? So this is the classical diagram of a pressure of temperature with the triple point, solid, liquid, and vapor. It is possible to do lyophilization or freeze drying when you sublimate the solid directly into gas. Then you avoid the capillary pressure. Okay, from the liquid to vapor evaporative drying, there will be the capillary pressure that will be developed, or there is another way to overcome the critical point, to increase temperature and pressure, and then your liquid will be in the supercritical state. In the supercritical state, the diffusivity is comparable. In fact, it is neither liquid nor gas. They have mixed properties. The diffusivity is comparable to gas. Density between the gas and the liquid has high solvation power. What is important for us is in supercritical state, there is no meniscus here, which is formed during evaporative drying. And thus, there is the zero capillary pressure. Thus, if you evacuate your liquid from the pores of the gel in the supercritical state, putting the liquid in the supercritical state, you hope that the pores will not collapse and you keep the morphology of your network, which is nanostructured. So just to repeat, to make a summary, if you are doing supercritical drying, usually CO2 is used because it has mild temperature and pressure conditions. What we are calling aerogel, usually you preserve the structure of the network. If you are doing freeze drying, usually it is done from water. When water is freezing, there are ice crystals that are growing. They are pushing the pores of the network, and they can completely deform the network, the structure of your gel. So, okay, there can be exceptions, but usually the morphology is not preserved. And as we said, okay, we are calling them xerogels, ambient pressure vacuum evaporative drying. There is a high chance that all pores will collapse. Obviously, the structure, the network formation will determine material properties, and I just want to show you the example of material that was obtained through freeze drying. It was starch, dissolved starch. You see the scale is 20 microns. So the pore size, that's a beautiful structure. It depends what you want to do in terms of application. But clearly the surface area will be low here compared to aerogel, which was obtained with supercritical drying. Here the scale is 100 nanometers. You see very fine network with small pores, and it will be a high surface area. So just a joke, polyurethane foams are not aerogels. There are a lot of speculations in literature. So how classical aerogels are made? We are not yet in bio-aerogels. Classical aerogels, you start with the precursor of small molecules. You do your chemistry, you obtain soil, you obtain the gel, cross-linking, whatever, and then you evacuate your liquid, and you obtain the aerogel. So classical aerogels are based on silica. Okay, there are some examples here. Can be metal oxide-based aerogels, can be based on synthetic polymers, and the common story, the common point in all these aerogels is you start with precursor, which is a monomer, that small molecule. So you have to do polymerization and cross-linking. What are the applications of aerogels? So I repeat the main properties are low density, small pore size, can be huge specific surface area. And the hottest application, the pre-industrial in the current state, is thermal insulation. There are companies that are doing this. You cannot buy in Castorama yet aerogels. They are very expensive, so it's at the pilot stage. And okay, there are American companies, there are Chinese companies, there is a small company, French company, Enersance, that are making aerogels in the shape of particles, blankets, or whatever different. And NASA in America have sent aerogels into space to collect the dust of the stars, which is a bit niche application, but why not? Because there is high specific surface area, so the dust of the stars was attached on the pores of the aerogel. Why aerogels they have very low thermal conductivity, which is called the thermal superinsulation. As you know, okay, not me to tell you the story. The thermal conductivity is roughly of a porous material is a sum of three components: conduction of the solid, conduction of the gas, and radiative. So if you want to decrease thermal conductivity, you need low density, as less as possible of the solid matter. Radiation for optically thick materials you can forget. Now, how to decrease the conductivity of the air, which is in the pores of our material? There is a Knudsen effect, which is saying that if the pore size is smaller than the mean free path of the air molecule between the collisions, and it is around 70 nanometers, 67 nanometers, then you have a confined air, and the conductivity of this confined air will be lower than the conductivity of the air around. And here you can play with this. You can have very low density, and you can have very small pore size where the conductivity of the air will be lower than the surrounding air. So this is the classical representation, usually when people are looking at the thermal conductivity of porous materials of aerogels, plotting conductivity as a function of density, and everybody is looking to find this minimum. And for silica aerogels, look at the characteristics. So here is the scale is 100 nanometers, the very small pore sizes, very porous material, low density, 0.1 gram per cubic centimeter, and the thermal conductivity is twice lower than the air. That's fantastic. That's a magic material. And so obviously the lower is thermal conductivity, the thinner will be the insulation layer. What is the story of the development of aerogels? It started a long time ago, almost 100 years ago, by American scientist Kistler in 1931. Then it was forgotten. Then there was interest in aerogels that was reborn when another chemistry was invented of silica. Then there was a birth of synthetic polymer aerogels. Then at the border between the 20th and 21st century, there was a huge breakthrough when ambient pressure silica aerogels were made, avoiding supercritical drying. That was a great thing, and this pushed industrial development of silica aerogels. So there is ongoing research on the improvement of mechanical properties of silica aerogels. People are trying to make synthetic polymer aerogels with ambient pressure drying, keeping super insulating properties. Partly working, not working very well now. To decrease the price of silica. So what's next? And next was the birth of bio-aerogels, bio-based aerogels, and there was the first European project at that time, and we made envelope solo in exactly 20 years ago. And we started working on cellulose aerogels. Now we are going to bio-aerogels. They are mainly based on polysaccharides for the time being. What are polysaccharides? The cellulose, amylose, amylopectin, which are the constituents of starch, alginate, carrageenan, pectin, chitosan. We are eating them. We have them on us. They are used in pharmaceutical applications. That's polysaccharides are all around us. So at the year 2000, there were 2-3 forgotten articles that we found after when people did supercritical drying of gels without really understanding what is going on. Scientifically, bioaerogels are very attractive because that allows making completely new biomaterials. And obviously the hot application, the first question we asked, can they be super insulating like silica aerogels? Can they be better or not? Now it is possible. There are publications that protein aerogels can be made and other bio-based matter. You may ask the question, why to bother to make bioaerogels while there are silica, which are very performing and synthetic polymer. Silica aerogels, to have them super insulating, the raw matter is still very expensive. And this is what is blocking the industrial development, despite that it is possible to not to use supercritical drying. Mechanical properties should be improved, but there are a lot of advancement. Synthetic polymer aerogels, some are thermal super insulating, not all. The starting matter is cheap. Mechanical properties are much better than silica aerogels, but synthesis is not very nice. It's using toxic matter, formaldehyde, and so on. And still there is a need in supercritical drying. So bioaerogels based, for example, on polysaccharides, that's renewable material coming from nature. Not expensive. There is no toxic compounds. I will show you how to make bioaerogels. So the question is, that's expense, can they be as good as synthetic or silica aerogels? This is what we will see. So how to make bio-based aerogels? This is this scheme as I showed you how to make synthetic polymer or silica aerogels. There is no this step, because in fact you start with ready polymers. You don't need any synthesis. You can dissolve polysaccharide, or you can make a suspension of nanocellulose or nanochitin. Then there are two pathways. You can make gelation, you can not make gelation. If you want to use drying with supercritical CO2, and the solvent of polysaccharides is usually not miscible with CO2, that usually is water. So you have to do solvent exchange step here. So there is no need in polymerization to start with ready polymers. There is maybe no need in gelation, so no cross-linking, no chemistry at all. There is a need in solvent exchange, but solvents are, okay, water, ethanol, that's reasonably reasonable. Okay, then we can discuss more details if you have questions. So obviously you must know well and master well the properties of starting polymers, because cellulose is not the same as starch, not the same as pectin, not the same as alginate. And now some properties in terms of thermal conductivity, but first I will show you that it is possible to make bio-aerogels in any shape. It depends, for example, if you're doing gelation, depends on the mold on the container where you are gelling the solutions. You can do 3D printing. You can do particles by dropping the solution in the gelling bath or in the coagulation bath. Different sizes for making droplets. You can use classical tools like atomization, preling, spraying, jet cutting, and each small particle will be small aerogel, as you see here the example so these are the particles of aerogels of the size of about 1 millimeter or 2 millimeters, low density, high specific surface area. And you can make even very small aerogel particles by emulsion. So again, here, each small particle, here the size is few tens of microns, low density, high specific surface area. So there is no limitations in making shapes. The mechanical properties are very good. These are the stress strain curves. Stress strain, you see, you can reach 70% of compression, as it is shown here, and bio-aerogels are not breaking. So this is very nice, and the compressive modulus is better than the silica aerogels for the same density. You see aerogels based on cellulose and on pectin have higher compressive modulus, so these are all positive things. Now what about thermal conductivity? We're coming to the point. For cellulose aerogels, we started to work with cellulose. So I will repeat now the plot, thermal conductivity as a function of density. And 0.025 is the conductivity, 0.025 watt per meter per Kelvin is the conductivity of the air. We did a lot of work on cellulose. So we were dissolving cellulose, making gels in different ways. We did not manage to go below the conductivity of the air. Why? Because if you look at the scanning electron microscopy images, you will see that the pore size is too high. Why cellulose is doing this? Nobody knows. Why it is making such gels that are with a large pore size, thicker pore walls, that it's not possible to go below the conductivity of the air. It's almost as the air, but no, not yet. Now, the first thermal superinsulating bio-aerogels were made 10 years ago. We were working, so we were desperate. I was desperate with cellulose, and we decided to change to another polysaccharide. At that time, there was not a lot of publications. I saw a few publications on pectin aerogels and with fine morphology. Nobody measured thermal conductivity. I said, let's try. We tried, and we got, here again, thermal conductivity as a function of density, and you see below the conductivity of the air, there are the values that are below, that are in the thermal superinsulating region. Why? Because that's low density, around 0.1, 0.05 gram per cubic centimeter, very fine morphology. The same year, in Japan, they did nanocellulose, nanofibrillated cellulose aerogels. We did not discuss, we were not project partners. We did not know what is going in another lab, but the same year they published also some values on the thermal conductivity of nanofibrillated cellulose aerogels below the conductivity of the air. These nanofibrillated cellulose aerogels were not made by cellulose dissolution. It was made in another way. Then we continued with pectin aerogels, and we got the dream in the U-shaped curve, the conductivity as a function of density. You see the U-shaped curve with a lot of points below the conductivity of the air. Then you can do gelation in different ways. You can vary, and all this is thanks to very fine network morphology. Now, we were still obsessed by cellulose. What we did to have low thermal conductivity, we filled cellulose gel with silica. We did hydrophobization, and we got interpenetrated cellulose silica aerogels. So initial cellulose aerogel here, low density, moderately high, okay, depends on the point of view, moderately high for aerogels, specific surface area, large pore sizes. The scale is 1 micron, large pore sizes. This is the silica aerogel with low conductivity, very high specific surface area, but very brittle. And then you have interpenetrated cellulose silica composite aerogel. The pores of cellulose were filled with silica, a bit higher density, huge surface area, and thermal conductivity below the conductivity of the air, and much better mechanical properties. Honestly, this is not industrial way to do, because to make a cellulose gel, to silica, supercritical drying, hydrophobization. But okay, that's one of potential way, as now is a bit too complicated. Now we continued, we are persistent. We decided to look what will happen with starch if we dissolve starch. So I remind you that starch is a mixture of amylose and amylopectin. Amylose is a linear polymer chain. Amylopectin is branched. Okay, branched chain. And here is the thermal conductivity, here as a function of amylose content, because in starch granules you can have very different ratio between amylose and amylopectin. So let's have a look one by one, and as usual, 0.025 is the conductivity of the air. And there are points, different points, above the conductivity of the air and below. So the first one, why it is high, rather high, thermal conductivity, because look at the morphology. Okay, density is low, specific surface area is low, and very rough morphology with large pores and very thick pore walls. This is the case of zero amylose, only amylopectin. They are gelling in different ways, in different kinetics. Again, if you have questions, I can explain. Then similar, regular potato, very rough morphology, large pore pores, large pore walls, high thermal conductivity. This one, this is close to the conductivity of the air, high amylose corn. Very fine morphology, look at fine morphology, much higher specific surface area. We're almost there. And the winner was the pea starch, which has the 40% of amylose and 60% of amylopectin, with very fine morphology, low density, and depending then on the concentration, on the way you prepare, some points can be above the conductivity of the air and some points are below the conductivity of the air. So starch aerogels can also be thermal superinsulating. What are remaining problems and what are the prospects? Obviously, to make it industrially relevant for thermal insulation, we have to avoid drying in supercritical conditions, because that's expensive and that's high pressure technology. So we recently discovered how to make cellulose aerogels avoiding supercritical drying. Dissolving in sodium hydroxide. Okay, we have some ideas why it is like this or like that. why it is preserving the network against the collapse during evaporative drying. However, cellulose aerogels are not super insulating. We are not yet there, okay? Now we went back to our winner, pectin aerogel. So thermal conductivity as a function of bulk density. So as I mentioned at the beginning, the thermal conductivity can be very low for pectin aerogels. This is the values of common insulating materials, but pectin is water soluble. If you leave in the air, it is catching the humidity and all the properties are vanishing. You have, okay. We did high relative humidity, but then you have increase in density, increase in thermal conductivity. So there is a PhD that is running now, Veleni, with the goal to make long-lasting, super-insulating pectin aerogels by different treatments, chemical vapor deposition, chemical grafting, modifications, and I will show you the only one successful result, which is the thermal conductivity here shown as a function of time. Okay, here it is, that's 2 months, but we now have more data. And with the interpenetrating network of pectin, which is coated with polyurea, you see that there are values that are stable. This is the conductivity of the air, again, 25. There are values that are stable for a long time, can be rather high hydrophobicity, low density, and stable thermal conductivity below the conductivity of the air. And now it is stable for 7 months. So polyurea is efficiently protecting pectin aerogels and stabilizing the properties. Still, we need supercritical drying. Okay, we're not yet there. With Fazia, we submitted a project that was not accepted to catch the both properties, but okay. So, to conclude, bioaerogels are still young materials. They are new materials with a lot of questions: how network structure is built, what are the correlations. Modeling is absolutely non-existent. For thermal conductivity, we have materials with thermal superinsulating. We have to avoid aging, and we have to avoid drying in supercritical conditions. These are the two areas that we are working on. There are other applications, not only thermal conductivity, because, for example, pectin aerogels, they are made without any toxic matter. The most toxic is ethanol, used for solvent exchange, which is okay. So they can be used in life science application, in cosmetics, in pharma, as carriers of active substances that can be released. We can eat them, for example, or we can put them as wound dressings. So there can be a lot of other interesting applications. The problem with bioaerogels is that they can cover very different areas. People are not speaking. I'm sorry, I don't know you. You are experts in thermal properties, and you don't know me. That's the problem to advance. So we have to speak different areas, as well as we did, for example, carbon based on aerogels. I knew nothing about electrochemical applications. People have to speak from different areas, have to speak with each other to advance. But this will create very interesting discoveries. So obviously the work was done by my PhD students and postdocs and trainees, and with colleagues participating, and okay, I was complaining on financing, but we were financed a bit by ANR, by Europe, by ADEM, but by CNRS, and I thank you for your attention.
Thank you very much. So we have now time for a few questions.
En anglais ou en français, comme vous voulez.
Voilà.
Ah ouais.
Thank you so much for this interesting talk. I like this subject. with bio-aerogels, maybe one of the most important features you get is flexibility. You loss of brittleness, which is nice because if you want to use materials, it's good to be brittle. But maybe on the opposite, because I've been working a lot on starch as well. By the way, we are using freeze drying of starch to make scaffolds, you know, Bio-Aerogels scaffolds, and we have seen the same structure as you, but it's micrometric, it's not nanometric. But maybe with starch, maybe one of the problems will be the ability of starch to keep up water. So the hygroscopic behavior should be very difficult, and with such small pores, you will get condensation
even
very
worse,
easily.
yes.
So the sorption isotherm should be quite interesting. Have you work obviously on sorption isotherm as well to see
for the time being,
how they will
we are working on
water?
pectin because it is the winner in terms of thermal
yes.
conductivity. But absolutely, you are right that we have to preserve against aging, whatever, either do packing or do hydrophobization, coating, or something has to be done.
I can feel this problem, but it's very nice.
Yes.
Have you? I have many questions, but have you worked on different solvents probably to make aerogels or bio-aerogels?
Evaporating solvents?
Yes.
Yes. This is what we did for cellulose. Obviously, if water has very high hypertension, to dry from water, nothing will work. To dry from ethanol works much better. We dried from hexane.
And with
works
ethanol,
well,
what you get as a result, because ethanol is a nice solvent, it's quite gentle solvent. So we like to work with ethanol.
Yes, absolutely.
Is it okay or not? It's not enough?
It is. It depends on the polysaccharide a lot. It depends on the solvent in which polysaccharide was dissolved. For example, for cellulose, we dissolved in sodium hydroxide, exchange it to ethanol and dried by evaporation from ethanol. It worked. When we dissolved cellulose in ionic liquid and did the same, it did not work.
Okay.
So there are a lot of factors that are influencing. That's still a lot of work.
And for freeze drying, as usual, it's a cooling phase, which is important.
Yes. Yes.
Did you succeed
there are publications
to reduce the pore size by cooling fast? Or this will be my last question because I have to let time for others.
There are publications that are using tert-butanol or mixture of tert-butanol water at the eutectic composition. When you are depressing the growth of the crystals, it works. But very few publications. And you need a freeze dryer which will be able to dry from tert-butanol. You have to. No, we don't have. No. But look, we build a project. Yes. Yes. But also, freeze drying is energy consuming. We can do it for pharma, for biomedical, which can be expensive. No, not for insulation. That was a question here. Bah, si vous voulez en français, en anglais, ça va aller. Même en russe.
Je vais poser ma question alors en français. Merci beaucoup pour votre présentation sur ce sujet dont j'ai beaucoup entendu parler. Et voilà, donc il y a eu pas mal de développement sur la partie bio, aérogel. Donc, en fait, vous parlez d'isolants, de super isolants. Et donc, les valeurs que vous obtenez, elles sont la moitié de celles de l'air, en gros. Est-ce que, on peut envisager de descendre encore en dessous, parce que des super isolants. Et quelles sont les limitations, parce que j'imagine qu'on peut se dire qu'on peut aller plus loin, puisqu'il faut réduire le libre parcours moyen des molécules d'air, puisque c'est ça, finalement.
Ouais. À ma connaissance, les meilleurs des meilleurs, c'est les aérogels de silice. Et le plus bas, c'est autour de 13 mW par mètre par Kelvin. En dessous, on arrive à panneaux sous vide. Les panneaux sous vide, c'est la conductivité thermique autour de 4-5 milliwatts par mètre par Kelvin. Maintenant, qu'est-ce que limite c'est quand même la densité. Il faut avoir le réseau solide. Si vous baissez trop la densité, vous augmentez la taille de port. Et donc, d'où cette courbe en U avec le minimum. Donc, il y a l'input de plusieurs, donc la conductivité de solide plus la densité augmente, la conductivité thermique monte. Avec le donc il y a trois parties solides, l'air et radiatif, et la somme donne ça. Donc ça descend pas comme ça, c'est fait le U, d'où la recherche de minimum. Et à ma connaissance, il n'y a pas de matériaux avec la conductivité plus basse que 12-13 milliwatts par mètre par Kelvin, parce qu'il y a le jeu entre tous les composants.
Est-ce que je peux poser encore une question? Alors sur la partie évacuer l'eau capillaire, là, est-ce que c'est beaucoup difficile de faire évaporer cette eau-là?
Il faut,
parce qu'il y a des pressions capillaires.
Il faut là si la question si la question est sur le voie avec le séchage supercritique, donc il faut faire un échange de solvants et il faut laver de l'eau. Donc l'eau n'est pas miscible avec CO2, donc il faut laver l'eau complètement en haut. On peut se permettre, je sais pas, il y a différentes approches, 1% peut-être au maximum. Donc, il faut, vous avez votre gel, il faut plonger dans l'éthanol. Il y aura l'échange par la diffusion. Vous prenez votre gel dans mélange l'eau-éthanol, dans le bain d'éthanol pur, et comme ça, plusieurs fois, il faut enlever l'eau. Donc, ça, c'est si vous avez le voie supercritique. Pareil pour si vous faites par évaporation de l'éthanol, aussi il faut éliminer l'eau dans tous les cas. Donc l'eau n'est pas bon pour séchage. Pour ça, oui. Ouais. Après,
merci.
Ça dépend d'application. Hein.
Ouais. Merci bien, merci.
Alors, merci pour votre présentation. Bon, vous m'avez fait un peu d'inspiration.
Rêver.
Alors, je vais
c'est magique. Hein,
voilà. Puisque vous avez travaillé sur les Bio-Aerogels, donc apparemment vous avez travaillé sur le cellulose, mais ma question, puisque je travaille aussi sur la pyrolyse des matériaux végétaux.
Oui, on a eu un projet. On a fait les aérogels à base de cellulose et après on a fait le pyrolyse. Donc on a enlevé. Pour cellulose, vous enlevez beaucoup de masse d'oxygène et d'hydrogène. Ouais. Donc pour rester le carbone, vous gardez 10% par rapport à la matière première. Donc il y a un shrinkage énorme. Ce qui était intéressant, je n'ai pas fait le slide, ce qui est intéressant et quand même, le matériau ne casse pas pendant le pyrolyse. Donc, si vous avez un cylindre, un gros cylindre au début, vous avez un petit cylindre de noir de carbone à la fin. Ça, c'est intéressant, avec surface spécifique autour de quelques centaines de mètres carrés par gramme et la taille de pore autour de... les petits macropores autour de quelques dizaines, 70 nanomètres, ce qui était intéressant. Pour application électrochimique, on a travaillé avec Saft, l'entreprise bordelaise qui fait les batteries. Et ils ont testé, on a fait nos disques de carbone, ils ont mis dans les piles boutons et ça marchait très bien.
Voilà.
Donc oui.
Donc pyrolyse, ça peut aller.
Ça marche,
voilà.
ça marche. Ouais,
bon, d'une manière générale, on fait la pyrolyse donc, de la matière végétale.
Juste, il faut respecter, il faut garder le plateau de température autour de 300 degrés,
300
je pense.
degrés, oui. Voilà.
Il faut pas augmenter la température.
Donc, on prend le résidu solide, le charbon, c'est-à-dire. Le charbon, parce que dans la pyrolyse, on peut avoir donc, la fraction solide. Sinon, on peut aussi prendre la fraction liquide, le bio-oil, qui est aussi un mélange de plusieurs. Donc là, vous travaillez sur la partie solide, donc le bio-charbon.
Oui, c'est un aérogel qui est complètement sec. Voilà. Complètement, oui. Pour les saccharides, c'est jamais
vous m'avez inspiré, alors dans ce cas-là, il y a des voies là-bas.
Oui, bien sûr. Il nous faut juste un petit financement pour continuer.
OK, merci beaucoup.
Il y avait la question.
On va l'avoir, le financement.
Merci pour votre présentation très intéressante. Au début, vous avez parlé qu'on peut utiliser aérogel comme le support catalytique. Est-ce que les bio-aérogels ils supportent les gradients thermiques jusqu'à quel...
Non, bien sûr. Plus que 100 degrés, ça ne tient pas très bien. Comme vous savez, la cellulose, tous les polysaccharides brûlent. Donc ça, des bio-aérogels, ce n'est pas pour application haute température, contrairement à la silice, évidemment, qui est un organique. Ah oui.
D'accord, ça ne tient pas du tout.
Non, ça ne tient pas du tout. Non.
D'accord.
Ça va brûler.
Et deuxième petite question, vous avez dit que c'est impossible d'avoir la distribution des pores. Donc, pourquoi ?
Parce que quand même, surtout par exemple pour la cellulose, la taille des pores varie de quelques dizaines de nanomètres jusqu'à quelques microns. Et pour couvrir toute la gamme, l'absorption d'azote ne marche pas. Je veux dire, vous pouvez faire, mais l'approche BGH qui est développée pour avoir la distribution de taille de pores marche pour les mésopores et petits macropores. Là, on sort de domaine de petits macropores. Et ce qu'on a vérifié plusieurs fois, avec l'absorption d'azote, la machine nous donne 20% de volume de pores. Donc la machine donne ce qu'elle peut donner. Mais on peut calculer le volume de pores avec la densité de squelette et la densité bulk. On peut estimer le volume de pores et la machine nous donne. Donc ça ne marche pas. Avec mercure, l'intrusion de mercure, sous pression, vos bio-aérogels se compressent. Donc là encore, la machine vous donne le volume en fonction de pression, mais ce n'est pas le volume que la mercure rentre, c'est le volume de diminution de votre échantillon.
Donc, ça veut dire aussi
il n'y a pas pour l'instant, c'est trop la gamme. Après, vous pouvez peut-être, il y a quelques publications en utilisant le DSC, mais là c'est homemade, tout ça. Donc voilà. Donc ça c'est un des difficultés et il faut développer.
Ok, merci.
Il y a une question là-bas aussi. Oui.
Bonjour. Une simple question. Vous parlez de l'isolation thermique et augmenter la surface d'échange. Est-ce que c'est un peu paradoxal ou non?
Non, je n'ai pas compris.
La surface d'échange.
Si vous allez vers la surface spécifique des pores. Oui.
Donc c'est la surface d'échange thermique.
OK.
Donc c'est un peu paradoxal ou non? Comment l'expliquer? Pour on augmente les surfaces d'échange, comme on savait, pour augmenter le transfert thermique.
Ouais.
Ici, on va vers les nanos, les pores nano, donc vous allez augmenter les surfaces d'échange.
Ah,
C'est un peu c'est spécifique. Donc, ce n'est pas les paramètres surface d'échange.
ah, l'échange de surface des pores, c'est ça la question?
Donc,
C'est les volumes spécifiques.
Ça prend beaucoup
Ok.
de chemin pour passer.
Oh, non, c'est juste... ok, je n'ai pas compris.
C'est l'effet Knudsen.
C'est- Très petite.
oui, mais elle a montré... oui, mais elle a montré de résultats avec des surfaces spécifiques plus importantes, mais de conductivité, moi ça prouve, ça prouve. Oui. Juste une petite question.
Ah, la surface d'échantillon. Ah, ok. Ouais. Ah oui. Ah oui, bien sûr. Oh, ok. Bon, merci. Et il y avait un jeune homme là-bas.
Juste petite question. Donc, vous avez montré, en fait... oui, c'est moi. Vous avez montré la stabilité des propriétés thermophysiques, donc la conductivité thermique pour 60 jours.
Plus, ok, ça c'est le biographe, maintenant 7 mois, mais
voilà,
ça ne suffit pas, hein, je suis consciente.
Alors, ma question, en fait, qu'en est-il pour des années? Est-ce qu'il y a des données...
Attendez, la durée de thèse est 3 ans, ok?
Oui, d'accord, non, mais à l'échelle l'applicatif, on cherche les années, nous.
Oui, je sais bien, oui, pour trouver,
là, bien.
pour trouver une bonne formulation, parce qu'il a fait plusieurs, on ne savait pas, il n'y a rien dans la littérature. Hein. Il a essayé différents types de hydrophobisation. Ah, ça c'est le 3e. Ok, on est contente que c'est 8 mois. Hein. La durée de thèse, on va continuer l'expérience jusqu'à la soutenance. Et après, voilà.
Bon, merci.
Voilà. Il y a un jeune homme là-bas. Va essayer de crier. À savoir qu'il n'y a rien dans la littérature hein, pour l'instant. Donc, bon, c'est déjà pas mal. Pour commencer. Oui.
Bonjour, je m'appelle Hamidi Bedraddin, je suis doctorant à l'université Gustave Eiffel et j'aimerais juste vous poser une question. Généralement, quand on ajoute le mot super, comme par exemple un écoulement sonique, on a un écoulement supersonique. Généralement, les lois changent et on arrive à des limitations. Donc, est-ce que là, pour les super isolants, est-ce qu'on n'arrive pas à la limitation des lois de Fourier, par exemple? Et est-ce qu'il y a une nouvelle hypothèse ou une nouvelle loi pour mesurer et calculer les conductivités thermiques? Merci.
Oui. Si on revient, c'était où? Pour la silice, je vous montre. Oui, il y a des limitations. Donc, voilà. C'est ça. Hein. Vous avez si c'est un matériau solide, vous avez là il y a des choses qui manquent. Hein. C'est très oui, ça c'est une approche très simple. Hein. Okay. mais vous avez le solide, le gaz et radiation. Ok. Donc c'est ça, les 3 composants plus les autres, comme collègue sait bien, c'est ça la limitation. Vous ne pouvez pas baisser à l'infini la conductivité. Il y a la conductivité de solide dans tous les cas.
Expérimentalement, comment est-ce qu'on peut mesurer la conductivité?
Il faut avoir... Il faut mesurer avec les précautions. Ouais. Il faut bien isoler votre matériau. Oui, vous pouvez mesurer.
Juste une réponse encore de thermicien. Dans ce cas-là, notre fourier est encore applicable. Alors on pourrait regarder ces modèles-là pour des biosphères parallèles. Là, c'est plutôt un modèle parallèle.
Oui, c'est très basique. C'est bien qu'il y a les débats. OK.
Très bien, merci beaucoup. Alors, moi, ça me fait penser à quelque chose parce que lorsque j'ai invité Tatiana pour faire cette conférence aux Journées internationales de thermique, elle m'a d'abord dit « Oui, mais je ne suis pas thermicienne, je ne sais pas si mes recherches peuvent intéresser la communauté des thermiciens. » Donc là, à observer les débats dans la salle, voilà, ça confirme que c'était, je pense, une excellente idée. Merci beaucoup.
Merci beaucoup
d'être venue.
Merci.